In the last lecture we had talked about structures, and also towards the end of the lecture we saw how we can write programs that read data from files and write data to files. Today we are going to talk about another very important tool in programming and constructing interesting data structures for holding various kinds of data, and that's dynamic memory allocation and linked lists. So to motivate the use of dynamic memory allocation, let's see what the problems in using arrays for storing large volumes of data are. Arrays let us store large numbers of data items, but as you know, we have to pre-specify a maximum limit. This maximum limit has to be declared at compile time, and we cannot change it at runtime. And if we have more data items at runtime as input than the specified limit, then we cannot really handle that. And if we specify a very large limit, then the problem is that we might end up wasting a lot of memory. So dynamic memory allocation, as the name suggests, allows us to ask the system for more memory as and when required. So we can essentially not allocate all memory at compile time itself. Instead, depending on the inputs, as and when more data items are needed to be stored, we can ask for more memory. For example, suppose we are reading a large set of data values, we can allocate memory for one item as and when we read a data item. We don't even need to know in advance how many data items are going to be there. But the problem with dynamic memory allocation is that we need to keep track of all these chunks of memory that we get dynamically allocated. Now in the case of an array, all the elements of the array are at contiguous memory locations. So if you know the address of the first element of the array, then it is easy to find the address of any array element, as we know, using pointer arithmetic or using the indexing mechanism for arrays. But when we dynamically allocate large number of chunks of memory one after the other, they are not guaranteed to be contiguous in memory, and therefore we have to somehow keep track of where these chunks of memory are in memory. And the solution to this particular problem is to use structures and pointers in combination. And the basic idea is very simple. Let's say we have integers as data items which we need to store, and we are using dynamic memory allocation to store them and allocate enough memory to hold an integer as and when we read an integer. So what we do is that each data item is stored in a structure which, besides containing the integer or whatever the type of our data item is, it will also contain a pointer to the structure containing the next data item. And so every structure will contain a pointer to the next structure containing the next data item, and that one will contain a pointer to the third structure, and so on and so forth. And as you can see, this creates a linked list of data items. Let's see it better through a pictorial representation. So in this example, again, we are assuming that it is integer values that we are interested in storing. So we have declared a structure type struct item which consists of an integer value and a pointer to another struct item. So note that inside a struct item I can't have another struct item, because then the size of this would have to be infinite, but I can always store a pointer to a similar kind of structure within a structure itself. So these kind of structures are called recursive structures, and that is possible because the size of a pointer is independent of the size of the quantity to which it points. So the compiler knows at compile time that an integer will take so many bytes and storing a pointer will require so many bytes, and therefore overall the structure will require so many bytes. And so we have this structure which consists of an integer value that we need to store and a pointer to the next structure. And let's say we have a variable p which is a pointer to an item. Now consider this kind of a linked list. So the variable p contains the pointer to the first element in the list. Each of these is an element, and each of these is of type struct item. So p contains a pointer to the first element, and the next field of the first element contains a pointer to the second element which has a value, and a pointer to the next element which again contains 3, and the pointer value in the next element is a null pointer, which we have already talked about earlier in some earlier lectures. This is a spatial pointer value, which is not the address of any legal memory location. So we can use this to mark the end of the list. But we have to be careful that we never dereference the null pointer. That is, we never perform a star operation or an arrow operation on a pointer which is null. Okay, so if we have this kind of a list, then we need to store only in a variable. We need to only store the starting address of the list or the pointer to the first element of the list, because the other elements can be tracked using these chain of pointers. So P is a pointer to the first element. So P arrow next will be a pointer to the second element, and similarly P arrow next will be a pointer to the third element, and so on and so forth. And similarly P arrow value is the data value of the first element, P arrow next arrow value is the data value of the second element, and P arrow next arrow value is the data value of the third element in the list, which is 3 in this particular case. Now, before we see how we can actually create a list, let's see an example where we actually go through this list and compute some quantity or look for something or something of that kind. So, as an example, let's assume we have such a list and we want to write a function which computes the average of the numbers in this list. And of course, it assumes that the number of elements is at least 1. So, this is the function prototype. We are going to return a float which is the average. The argument is a P which is of type struct item star. So the argument is supposed to be a pointer to the first element of the list for which we want to compute the average. So we have two local variables. Sum will represent the sum of the data values in the list, and count will represent the number of elements in the list. Now this loop essentially traverses the list. As long as P is not null, in every step we make P point to the next element in the list, and the element that it was pointing to, we add that data value to sum and increment count by 1. So as long as P is not null, P arrow value is added to sum, count is incremented by 1, and then P is made to point to the next element of the list, and finally P will become null because the last element of the list will have the next value null. At that time this loop will terminate, and then sum will be the sum of all the elements in the list, count will be the number of elements in the list, and therefore sum divided by count will be the average. So let's see with an example how this executes. So in this example, in the main function we have somehow created the list, which we haven't seen so far. We'll look at that shortly. And let's assume that P points to the first element of the list. Let's again assume that this is what the list looks like. So this variable P is the variable P in main. Now when the function average is called, as you know, space is going to be created for the parameter P of average, and the variables sum and count, which are local variables of average, and the parameter P will be initialized with the value of the argument, which is this P, and therefore that will be a pointer to the first element of the list as well. So space for P is created, is initialized to the value of this P, which is a pointer to the first element. So this P also gets a pointer to the first element in the list. Now let's go through the loop. P is not null, and so therefore this loop will execute, loop body will execute, sum will become, so initially first of course the sum and count are initialized to 0. Now the first time around the loop executes, sum will become 5, count will become 1, and P will become P arrow next. Now P is currently pointing to this element, and P arrow next is this value, which is nothing but a pointer to the second element. So when this statement executes, P will now be pointing to the second element of the list. That's what happens. Sum becomes 5, count becomes 1. Again P is not null, so the next time around sum becomes 12, count becomes 2, and P now points to the third element of the list. Again P is not null, so sum becomes 15, count becomes 3, and now P becomes null because P was this and P arrow next was null. So now P has become null, and so the loop terminates, and sum divided by count is of course 5, so 5 will be returned. Let's see now how a list can be created. So essentially in this example of seeing how we can create a list, whenever we read a data item, we are going to allocate a memory chunk large enough to hold a struct item and store the data item in that field. Now, for allocating memory of a given size, we are going to use the library called malloc, which is the library call used for dynamic memory allocation. So once we have allocated the memory for a struct item dynamically, then we initialize the data value in that to the value that we just read as input, and the list that we already have, we insert this new item in the existing list. So in the first example that we are going to see, what we are going to do is that the new data item that we read will be inserted in the beginning of the list that is already there. So let's see the code to do that. Well, first, for using the malloc function, you need to include the file stdlib.h. So that has to be included in all programs that use malloc. Now, here is the function createList, which will create a list of read a number of data items from the input and create a linked list of those data items. And what it returns is a struct item star, which means that it will return the pointer to the first element of this list, which is going to get created. Now, these are the local variables. List is a local variable which is again of type struct item star. So, and it is initialized to null, and that's because currently the list is empty, and so therefore we have made the pointer list point to null, and p will point to the structure that we dynamically allocate every time, and value is the value that we read. Now, as long as reading an integer results in success, scanf returns 1, what we do is we allocate a chunk of memory using malloc. The argument to malloc is the size in bytes that we want to of the memory chunk that we want to allocate. Now, recall that the size of any type can be obtained using the size of operator in C. So, size of struct item gives us the number of size in number of bytes of the type struct item. So, that's the number of bytes that we dynamically want to allocate. So, we specify that integer as the argument to malloc. What malloc returns is a pointer to this dynamically allocated structure. But if for some reason memory allocation fails, for example, if we have allocated so much memory dynamically that the system has run out of memory, then malloc returns null. So, it's important that whenever we use malloc, we check that the return value is not null, because if we are careless and we use up too much memory, then malloc might return null. So, if p is null, we print some error message and exit. So, assuming p is not null, we set p value of p to the value that we read here, and these two are inserting this new element in the list. Let's see how exactly that's happening. And finally, when this loop terminates, that is when we couldn't read any more integer values, then we return list. Now, let's see how exactly all this is really happening. So, we have these variables list and p. List is initialized to null, p is not initialized. Let's say the first data value that we read is 1. So, this allocates a new structure for this and stores the pointer to this structure in p. So, this is what happens, and then we store the value that we read in the value field of this structure. Now, p arrow next is list. Now, the value of list right now is null, so p arrow next will also become null. So, that means this value, the next field of this structure, becomes null, and the next statement is list assigned p, which means that list is no longer null, list is now pointing to this element. Now, let's assume that we read one more integer value, and let's say we happen to read the value 3. So, again p is assigned malloc a structure of size struct item. So, again another structure of the same size is allocated somewhere in the memory, and now p is pointing to this, and p arrow value is initialized to 3. P arrow next this time is list. So, what is being done is that this next field of this new element is being made to point to the first element of the existing list. So now this 3 becomes the first element of the list, and therefore the value of list is changed to point to this new first element, and so on. So when the next value is read, another structure will be created, and let's say 5 is read, and the next field will be made to point to the first element of the currently existing list, and the list pointer will be updated to point to this first element, so that this will become the first element. So if you, at the end of this, if we write 1, 3, 5, the list will look like this. Please go through this example once again to make sure that you understand exactly what is happening here, and finally the value of list is returned. Okay, now so in this code, what was happening is that the order of elements in the list is reverse of the order of elements of the order in which the values were read. Now suppose we want to create the list in which the elements are in the same order as the order in which they were read. Now what do we have to do for achieving that? What we'll have to make sure is that if we have an existing list of let's say 3 items, one, 3, 5, this is null, and we want to insert 7. So this is a pointer to the first element in the list. Let's call it the head of the list. And now when we, let's say, read 7, now this element must be inserted at the end of the list. So that means this pointer value must be updated to point to this, and this pointer value must be made null. So therefore, if we want to update this field of this structure, we must somehow obtain a pointer to this structure. Now one way to do that could be to traverse this list once again and reach the last element, and then set the next field of that element to the newly allocated structure, but obviously that is going to be expensive. What is better is that we maintain a pointer to the last element of the list, and when we insert one more element, since we already have the tail pointer, all we have to do is set the next field in the structure pointed to by the tail pointer to the newly allocated structure, and update tail to point to this structure, and that's what is going to happen in the code that we just saw, that we are just going to see. But we have to be careful, because if initially the list is empty, so both head and tail are going to be null. So if we try to set tail arrow next to P, where P is the pointer to the newly allocated element, then if the value of tail is null, then we are dereferencing a null pointer, which will result in unpredictable behavior, which will probably cause the program to crash, and so this must not be done, and therefore we need to specially consider the case when inserting the first item in the list. So let's look at the code. So we initialize head and tail to null, and P will be the pointer to the newly allocated element. Value is as before, so we read a value, and we allocate a new structure for holding this value. So if P is null, we print an error message and exit, etc. So this P points to the new value, to the new structure that has been allocated. The value field is set to whatever value we read, let's say 10. The next field is set to null, and now there are two cases. If tail is null, that means that this is going to be the first element in the list, and so head and tail are both set to P, because this is the first as well as the last element of the list. Now if tail is not null, then tail is pointing to an existing last element of the list. The list has at least one element. Let's say this happened to be 5. So we say set tail arrow next to P, which means this tail arrow next was null initially, so we make it now point to the newly allocated structure, and tail is set to P, so that now tail also points here, because this element is now the last element in the list. Okay, let's now consider some other operations on a linked list that we might want to perform. We might want to insert an element in the list, and we might want to delete an element in the list. Now when we delete an element from the list, then we also need to free or deallocate the memory assigned to this particular element in the list, because if we do not do that, then what might happen is that we keep allocating more and more memory without deallocating any memory, and ultimately we might run out of memory. So it's a good practice to always free or deallocate memory as soon as it is no longer required, and we'll see how to do that. Now when we want to insert or delete an element in the list, you can see that the value of the next field in the previous element is going to change. So for example, if we have this list, let's say 5, 3, this is, and we want to delete this element from the list, then what's going to happen is that this value must be changed to this value so that this structure is no longer part of the list. So therefore, if we want to modify this value, we must have a pointer to this element of the list. So that means we must have a pointer to the element before the one that has to be deleted. And similarly, when we want to insert an element in the list, so let's say this is something like the following. Now suppose we want to insert an element between these two elements, let's say 6. So we allocate a new structure. Now what's going to happen is that this value, the value of next in the element before the position of the inserted element, must be changed to point to this. This must be changed to point to the next element in the list. Now if we have a pointer to this, then we can always obtain a pointer to the next element in the list. But if we have a pointer to a particular element in the list, we cannot obtain easily the pointer to the previous element in the list. So therefore, for both insertion and deletion, what is easy to do is to assume that we are given a pointer to the element in the list just before the element which has to be deleted, or just before the place where the element has to be inserted. And the third operation that we'll consider will be to free the entire list. So if we are done with the entire list as a whole, we want to delete or deallocate all the elements of the list, then we'll have to go through the list and deallocate each structure in the list, each element in the list individually. So we'll look at code snippets to do all these three operations. So let's take the first operation, that is insertion of an element after a given element in the list. So here is what the code might look like. So let's assume that list is the pointer to the first element in the list, and P is the pointer to the element after which the new element has to be inserted, and V is the data value for the new element. So that means that list is pointer to the first element in the list, and P is a pointer to the element in the list after which this element has to be inserted. So let's take an example. Maybe this is null, and this is list is pointer to the first element in the list, and let's say we want to insert the new element here. So P is a pointer to the element just before that. So the insertion is quite straightforward. We have to of course allocate a new structure, and we do that and store the pointer to that structure in the variable new, set the value to V, the value that needs to be inserted. So let's just put the value V here. Now let's assume that P is not null. If P is null, we'll assume that what we want to do is to insert the new element as the first element in the list, and that again we'll have to specially handle because we cannot dereference the pointer, the null pointer. Let's assume for the minute that P is not null, so we execute this piece of code. So what happens is that new arrow next is set P arrow next. Now P is pointing to this structure, and the value of P arrow next is pointer to this structure. So new arrow next, which is this box, gets assigned a pointer to the element in the list after P, and finally P arrow next is assigned new. Now this structure P, the next element that it should point to is the new structure. So this is changed to point to new. So essentially now the list looks like 1 followed by 3 followed by V followed by 5 followed by whatever else which might have been null. Now the second case is when we want to insert the new element as the first element in the list, and let's assume that in that case the value of P is specified as null. So if P is null, that means that we want to insert the new element as the very first element in the list. Let's assume that this is the existing list and we want to insert the value 1, let us say. So in this case P is null. So in this case what's going to happen is that the value of the variable list itself needs to change, because list, remember, by convention will always point to the first element, and the new element will become the first element, and the next field of the new element must point to what will become the second element, and therefore what is currently the first element of the list. So new arrow next is new arrow next is assigned null. So the value of new arrow next should be set to the current value of list. In fact, there is a mistake here. This should be list here. And finally list is set to point to the new element, to which new is a pointer, so list is just assigned new. So that inserts the element in the list after the element P. Let's now look at deletion from a list, and again we assume that list points to the first element in the list, and P is a pointer to the element, the one after which the element after the one pointed to by P has to be deleted. So again, taking an example, if we want to delete this element, then we'll set P to this, and if we want to delete the third element, we'll assume that P points to the second element. So we are assuming that P is pointing to the element, the one after which has to be deleted. Now again, if P is null, then we are assuming that the first item in the list should be deleted. So because if P points to the first element itself, then the second element will get deleted. So if P is null, then what should be done is that list should point to the second element of the list, to the second element of the existing list, and the first element should be the first structure should be deallocated, memory should be freed. So now what we are doing is that we are using the variable Q to point to the element which is being removed from the list, so that we can free the memory being assigned to this element. So Q is set to list if P is null. Remember that if P is null, let's say P is null, so if P is null, then the very first element of the list has to be deleted. So Q is made to point to the list. So Q will always point to the element which is going to be deleted, and list is assigned list arrow next. So because the second element in the previous in the existing list now becomes the first element, and list arrow next is a pointer to the second element, so list is changed to point to the second element. Now this element is no longer in the list, but we still have a pointer to this in the variable Q. Now if P is not null, that means we do not want to delete the very first element in the list. So let's assume as an example that we want to delete the second element in the list. So in this case, if we want to delete the second element in the list, both list and P are pointing to the first element. Now what should happen is essentially that this pointer should bypass the structure and point directly to the third element. So first we set Q to point to the element which is to be deleted, and which will always be P arrow next, because the element next to P has to be deleted, so Q is set to that, and P arrow next is set to Q arrow next. So P arrow next is this box, and the value of that will become Q arrow next, which is this pointer. So essentially this pointer is removed and it points directly over here. So this element has now been removed from the list, but again we have a pointer to this element in the form of Q. Finally, once we have removed the element from the list, we must, as I said, free the memory allocated to the deleted item. So to do that, we use the library called free. It does not return anything, and the argument is simply a pointer to the chunk of memory which you want to delete. You must be very careful that the pointer that you supply must point to a chunk of memory which was dynamically allocated using malloc. You cannot, for example, if you specify the address of some variable in the memory in the program, then this will have very unpredictable results. And also, once a chunk of memory has been freed, now the pointer q to that chunk of memory must not be dereferenced, because it is now pointing to a chunk of memory which has been deallocated. So we'll in the next example see the consequences of how that might erroneously happen and what might happen in that case. So next what we are going to do is to try and free the entire list. So we are writing a function free list which takes a pointer to the first element in the list and frees the entire list. That is, essentially it is going to traverse the list, and each element in the list is going to be freed. So memory assigned to each element in the list is being deallocated. So this is our first attempt at writing this function, and as this comment shows, there is something wrong with this. So what we do is traverse the list again using the same kind of a while loop. While p is not null, we free p and then assign p to point to the next element in the list. Now what is wrong with this code is that p is being dereferenced here after it has been freed. So a chunk of memory has been freed, so it no longer exists. And now if we try to dereference a pointer pointing to this, remember that p arrow next is exactly the same as star p dot next. So we are dereferencing p, which is pointing to a piece of memory which has been deallocated, and that will lead to unpredictable results. So let's see that more precisely through an example. Let's assume that p is pointing to the first element in this list, 5, 7 and 3. Now p is not null, so the first time around the loop executes. Free p will essentially deallocate this structure to which a pointer is being supplied as argument. So this structure ceases to exist in some sense. Now you can see that p is pointing to a structure which no longer exists, and such a pointer is called a dangling pointer. And now when we try to find p arrow next, that will result in unpredictable behavior. And that's because the value of p is what is known as a dangling pointer. It is not pointing to a valid region in the memory. So this is the correct version. What we have to make sure essentially is that we don't dereference a pointer once we have freed the memory pointed to by that pointer. So what we are doing is that we do p assign p arrow next before doing the freeing, but if we do p assign p arrow next, then we have already lost the old value of p. So what we do is store the old value of p in q and then use free q instead. So that's exactly the same as before, except that the dereferencing of a dangling pointer is not happening. Let's see how it is going to execute. So let's again assume that p points to the first element in this list, and now p is not null, so the loop body executes. Q is assigned p, then p is assigned p arrow next, so p points to the second element. Now free q happens, so the first element gets deallocated. Now p is still not null, so we go back to the loop condition. P is still not null, so the loop body will execute once more. Q is again assigned p, so q now points to the second element. P is assigned p arrow next, and then free q, so the second element gets deallocated. And then p is still not null, so we'll execute the loop one more time. Q is assigned p, p is assigned p arrow next. P arrow next in this case is null, so p becomes null, and free q results in this being last structure being deallocated, and so the entire list has been freed. Now to summarize, there are two common problems with dynamic memory allocation, and you'll find that unless you're careful, you will easily make these mistakes, and one has to be extra careful against these kind of mistakes. The first kind of problem results when we do not free a dynamically allocated chunk of memory even when we are finished using this. So such a chunk of memory is called garbage appropriately, because it is still in the it is still not freed, so it cannot be reused, but it is not useful either. So this leads to what are known as memory leaks. Essentially what happens is that a program keeps on allocating memory, but if it doesn't free memory, then ultimately it might run out of memory, and that's like, you know, having the memory leaked away. And the solution to this problem, of course, is to be careful and deallocate any memory chunk as soon as its use is over. And the second problem that we just saw is the problem of dangling pointer. That is a pointer that points to a chunk of memory that has been deallocated, and as we saw, dereferencing a dangling pointer causes unpredictable behavior, and the only way to avoid this is to make sure that a dangling pointer is never dereferenced, and we must always be careful not to do that. So that's the end of today's lecture, and as a matter of fact, this was the last lecture in the course, so that's the end of the course as well, and I hope that you found the course both useful as well as interesting. But before I take your leave, I would like to remind you that programming is not something that you can learn by reading a book or by watching videos. The only way you can learn to program is to actually write programs, and not just on paper, but also try out things actually on a computer. You will certainly make mistakes, and it's those mistakes that, of course, that one learns from. So write a lot of programs, have fun doing it, and thank you for watching this series.